Ready?
The broadcast is now starting. All attendees are in listen-only mode.
Welcome to today's webinar, Maximizing Transformer Reliability While Minimizing Maintenance Spending. My name is Lelania Corsis, and I'm with ABB. I'll be moderating today's webinar. Before we get started, I'd like to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question, please use the question box on the GoToWebinar panel. We will try to answer your questions during the event. Today's webinar is being recorded. A link to the recording and the slide deck will be emailed to you following today's event. Please feel free to forward the link to people you know who could benefit from the presentation. Before we get to our feature presentation, I'd like to introduce the ABB Automation and Power World event. This year's event will be held March 25th through 28th at the Orange County Convention Center in Orlando, Florida. Automation and Power World is the premier event for engineers and business leaders designed so you can experience and learn the latest in automation and power technology and how it can benefit the profitability of your business. This mega event will include over 400 educational workshops on topics that are vital to the success of your business. Today's webinar will give you an example of the type of practical training you'll experience at the event. You can earn PDH and CEU credits and spend valuable networking time with your peers. The event will also feature a technology and solution center with over 150,000 square feet of exhibits with nearly 100 tons of electrical gear and hundreds of experts ready to answer any of your questions and share the future of automation and power solutions. We are expecting over 4,000 attendees at this event, making it an excellent opportunity for face-to-face sharing of ideas and a chance to get reacquainted with old friends and colleagues. Here are some of the examples of the educational workshops developed for all audiences, roles, industries, and experience levels. Be sure to bring your questions and get them answered by our panel of experts. Here are some comments from past attendees. I'll be back at the end of today's presentation with more information about ABB Automation and Power World Conference. Now I'd like to introduce today's speaker, Craig Stegmeyer. Craig Stegmeyer is the Business Development and Technology Director for ABB's North American Transformer Remanufacturing and Engineering Services Organization, or TRES. He's responsible for developing effective processes, supporting condition evaluation and assessment tools, life extension solutions, and training programs for utility and industrial users of power transformers. Formerly, he was the Engineering Solutions Manager for TRES North America, leading a group responsible for transformer fleet assessment, engineering solutions, and design and operation studies that assist U.S., Canadian, and Mexican customers in reliably operating power transformers. His experience also includes transformer diagnostics, as well as transformer and transformer component design and development.
Thanks, Lelania.
You're welcome.
Good afternoon, everybody. We're going to spend a few minutes, or maybe 30 or 35 of them, talking about transformer reliability. We've got a situation in the industry where basically, I'm trying to advance the slide. Okay, where we have an infrastructure of old power transformers. There are some new transformers being purchased and deployed all the time, but the reality is that a lot of transformers are fairly old, and in fact the average age is up over 40 years. We've got a lot of people who purchase those transformers and have lived with those transformers that aren't around anymore. They've retired. They haven't been replaced. There's been changes. And so we see that those folks aren't there. Big transformers are costly. Otherwise, everybody would probably take their 40-year-old transformer when it turned 30 and they would have replaced it. But the reality is these things wind well if they've lived for 30 years and they're not worked too hard. they may still have another 30 years of life in them. But the challenge for everybody is to figure out how to get that life out of them, how to understand the condition of the transformer. And that's really what the gist of this webinar is going to cover. The complexity of the grid is ever increasing, and so the way the transformer is used is probably different than when it was purchased 30 or 40 years ago. And then, of course, we've got a lot of smart grid and reliability initiatives taking place, and we want to make sure our power transformers last and continue to provide reliable service. Now, there's a lot of smart grid building blocks that have kind of come of age. And it's given us a chance to learn more about our transformers than we used to. In the old days, we had SCADA systems, may have controlled a tap changer remotely, may have got a couple of basic pieces of information from the transformer, but there really wasn't an ongoing stream of information coming in. And to understand a transformer and what condition it's in, it's a puzzle of a lot of pieces. And as we start to develop tools now that let us assemble those pieces, whether it's a distribution transformer, whether it's a large power transformer, we're able to much better understand and collect this data so that we wind up being able to determine the condition of the transformer. And we're going to get into how to dynamically deal with that data a little later in the presentation. But this is just kind of a basic building block as to where we get started. Now, in terms of the Transformer Assessor's Toolbox, again, in the old days, you took an oil sample, you cut the power to the transformer and did a power factor and capacitance test on the main transformer and the windings. You really didn't want to get too intrusive on your transformer. In fact, statistics show that if you mess with the transformer, there's a chance you're going to mess it up, so you really don't want to touch it unless you're going to do something positive for the transformer. So, and now we've got data collection devices, and that ranges everything from temperature gauges to sensors on bushings and literally online gas chromatographs that are constantly sampling the oil on the transformer. The utility or our industrial customer that owns the transformer has fewer people than ever to deal with their fleet, and so data is being collected at an ever-increasing rate. Oh, that's an interesting thing. I guess we ought to defer that action, Lilina, huh? Lilina? Okay, well, I'll keep talking to this. Okay, sorry about that. And so we've got this data from electronic devices that are starting to collect data for us, and again, everything from temperature to bushing sensors to sophisticated gas chromatographs, and it's assembling in very large piles. And how does the utility engineer deal with those piles of data? Well, we have a fleet assessment process that's really been honed over 700 years now. Obviously, Westinghouse and Tom Edison and Nikola Tesla didn't come up, and can't forget William Stanley, didn't come up with the transformer concept 700 years ago, but there's a lot of brands that are now part of the ABB group. That gives us a lot of lessons learned, both in the good and the bad range, and so we've got a lot of design and manufacturing experience that's let us learn the many different ways a transformer can be built, and in all honesty, the many different ways end of life can come about for a power transformer. Our condition assessment tools have been developed over the course of the last decade through the use of them to literally assess transformers around the world. We have expertise in some key testing. This is where you don't have to go inside the transformer to figure out what's going on inside the transformer. And of course, you know, for years we've been using oil samples, we've been using DGA, but some of the stuff that's occurred in the last decade or so, frequency response analysis or swept frequency response analysis, dielectric spectroscopy, which no normal person can pronounce spectroscopy, so we call it dielectric frequency response, and we're trying to develop other tools like that. Our mature transformer management program, we've literally assessed more than 10,000 transformers around the globe, more than 3,000 here in North America. And all this, again, we got the data, we got the tools, but we've been able to marry it together. ABB purchased a company named Ventex, which has a product called Focal Point that gives us great visibility of the system. They focus primarily in distribution management, but as we are able to handle the collection of this data, we're getting into the mode of power transformer management. So I hit my down button too much there, sorry. A good condition assessment program has to include a series of parameters and a series of steps in the condition assessment program. So our mature transformer management program initially does a broad fleet risk screen on the transformers so that you can identify the transformers that are behaving well, and you can focus your efforts on the transformers that aren't. Once you identify those transformers maybe that are not operating within normal parameters, we get into a phase 2, and there we look at the transformer in detail or more detail, and we determine what the issues are that the transformer is having, and we try to work with customers to come up with value-driven actions that let those issues be taken care of. And of course, a lot of these, I mean, you may have a cooling system, for example. The core and coils of the transformer can last 50, 60 years, but a lot of times fans, pumps, even the radiators themselves might need to be replaced partway through that. And you don't want to spend several $100,000 on a transformer that has a core and coil at the end of life. So we always suggest some life profiling before a lot of money gets spent, and then implementation of whatever tools we determine are necessary, whatever actions are necessary to bring the transformer back into health. Now, in the risk of failure assessment, we look at 3 prime things that happen inside your transformer. The first 3 bullets, we have the risk of short circuit failure, that if you have a through fault in the transformer or through the transformer, it produces terrific forces because the currents are much higher than the normal load current in the transformer. They vary by the square of the current. A transformer basically is modeled by an electrical engineer as a locked rotor motor, and so all those windings want to start moving during a short circuit. Anybody who's been in a substation on a hot summer day or even a cold winter day understands transformers put out heat. They have waste losses. Transformers are extremely efficient machines. In fact, they're probably the most efficient machine on earth. They're 99.8% or higher in efficiency, so there's very little loss. But what loss does occur quite often shows up in heat. And that heat, unfortunately, for the organic materials and some of the polymeric materials in the transformer actually contribute to their end of life. They cause breakdown to occur. And so if the thermal condition of the transformer isn't so good, if you got a cooling system that's not quite up to where it should be, there's going to be problems with that transformer. And of course, the dielectric failure is another point of risk where the transformer can be damaged from lightning strikes, switching surges, other dielectric events occurring on the system. Now, accessory failures, and Doble put out a few years ago that between bushings and tap changers, about 35% of transformer failures happen by accessories. So you can't forget that when you're doing a good, solid condition assessment. And then, of course, there are other system-based events, maybe relaying practices, maybe susceptibility to geomagnetic disturbances, sort of location or environmental events, whether you're in a tornado or hurricane-prone area, for example, that could damage the transformer. So you've got to look at all 5 of these things if you're going to have a solid condition assessment program. The current status of our program is we look at more than different parameters, input data, that traditionally has been collected manually pretty much and entered into databases at best, sometimes just sitting in file drawers. So we look at that information. We go through the 5 risk categories and use some or all of those pieces of information to calculate each type of different risk. And then we come up with an aggregate risk of failure for the power transformer. And what that does is, you know, it's the old adage, how do you eat an elephant? Well, the answer is a bite at a time. You got a big fleet of transformers. If you do this and you come up with a risk of failure, it gives you a chance to determine what transformers are really in the worst shape and would benefit the most from your attention. And that's what is really the hallmark of our fleet assessment process. Not all 64 of those items are required to do a condition assessment of a transformer. The ones that are listed in red on this slide are the items that we consider very essential to be able to get some kind of a good baseline position of what the transformer's reliability is. You know, I mentioned bushings, oil preservation systems, cooling systems, LTCs. All of those things are important to look at. And what's really critical is that you understand the design of a specific transformer. It's just like any of the people on this call. We have different DNA. Truly, we're going to fail eventually in different ways. And transformers are the same way. The manufacturer produced maybe the issues and the understanding and the state of the art at that manufacturer at the time all put limitations on how long that transformer is going to last. And so what we want to do is have a condition evaluation program that's design-based. It considers the oil preservation system. It considers the materials in the transformer. We're seeing transformers today. We always used to assume they were copper with paper wrapped around the copper. We're seeing transformers today made with copper with an enamel on the copper. And so the breakdown characteristic and even the oil samples that you analyze will be completely different chemistry. So you have to know what chemistry, what are the materials inside your transformer that just simply are breaking down as you use your transformer, go through the life of your transformer, and by understanding those materials, you're able to understand really what the condition of the power transformer is. Risk of failure is one item, but the importance of the transformer is another key aspect that you have to look at. So just knowing your transformer is a little unreliable. If you've got 3 or 4 ways around that transformer in order to deliver power to your customers, that's not nearly as urgent as, say, a generator step-up transformer that if you lose that, the power plant goes down. And as unfortunately the tsunami showed us, if you have auxiliary transformers that run key systems in your plants, those transformers may be small. They may only be 10, 20, 30 MVA, but they might be critical to the operation or even the safety of a nuclear power plant. So you got to combine your risk of failure and the importance, and of course it's up to you, the customer, to determine the importance. We'll help out with the risk of failure. And you can see our little cone there that popped up on the screen. That will tell us for any specific transformer, and we've just pulled one out of there that had almost a 6% risk of failure, that you can see it has some real issues with high temperature and from mechanical rigidity in terms of short circuit strength. So that lets the transformer assessor start to focus on what's going on with that particular transformer. So again, to kind of summarize, step 1 is a broad fleet screen that identifies the transformers, and you know, the gray is kind of the gray box. They're unknown, and once we take a look at some data on the transformer, how it's been performing for you, some conditional information, oil samples, and power factor capacitance tests, that sort of thing, then we can start coloring those transformers either red, yellow, or green. The green ones we don't want you to neglect. We want you to go back and do your power factor and capacitance and sample oil from them next year, but basically they're operating in a healthy state. However, the ones that are yellow, and especially the ones that are red, they do need action to them. And what you want to do in step 2 is go through a detailed design by design, transformer by transformer review of that information and come up with actions that are going to help the transformer get more reliable. We can't always turn the red unreliable transformers into green ones, but that is certainly the objective, and we're going to try to come up with solutions. You may not believe this. I mean, I work for a transformer service organization, and when we initially started this more than 10 years ago, people said, oh, you're a service organization, you're just going to want to sell services. But the reality is we're actually trying to minimize the dollars you spend on service, but to maximize the effectiveness of those dollars. And so that's really what any assessment process, whoever does your transformer assessments, you need to ask them the kind of questions that we're going over here and make sure that it's an effective asset assessment process. And then once you understand the condition of those transformers, depending whether they're relatively new and you're pretty certain there's a lot of life left in that transformer, or if your transformer is 40, 50, 70 years old, you're going to come up with different actions. But it gives you a chance to come up with a long-term strategy that gives you a chance to really take actions on your transformer that are going to maximize the life on the power transformer. While we wait for this slide to change. Hope I didn't just go by 2. Okay. This is a graphic that shows all of the transformers we've assessed in North America. And the good news here, the old 80-20 or 90-10 principle really does apply. In terms of importance of the transformer, you can see that on the closest axis to our left, and to our right is the risk of failure. And you can see those green bars are very tall. Some have 120 or so transformers in them. So the good news is the transformers we've assessed, a lot of them are in good condition, ready to continue or provide continued reliable service, and you don't have to worry too much about those. You can see there's a little more in the yellow bars than certainly the red bars, but the red ones are the ones that really let everybody develop a laser-like focus on transformers and take actions that are going to make those transformers more reliable. What we want to do now is get to the point where that used to be pretty much a static snapshot. We've now got algorithms that were developed, again, with that static snapshot, but we've got dynamically changing information. Every day your transformer ages a day closer to its end of life. And so what we want to make sure is that any new data that comes in, that you have a process or you have a way to deal with that data so that you don't have to keep taking frequent snapshots. So you, in essence, have something that allows you to look at your fleet, look at your enterprise, and know which transformers are behaving reliably and which ones are having issues. So in the old days, you'd have a SCADA system collecting some data. You'd have the site take a picture, in essence, of what's going on the site. They'd provide it to us. We'd deliver a report back to the site, and just like any single point snapshot and a good condition assessment, we have a lot of confidence, and most of our customers have a lot of confidence in our MTMP program. But the reality is it's that single point snapshot sort of approach. Well, we've now figured out how to take those algorithms, embed them on your site, on your transformers, your databases, so that we can wind up continually analyzing your transformers so that as new information becomes available, and this isn't, in essence, a pitch telling you need to put online monitoring there. Any new information that becomes available, if somebody goes out and takes an oil sample, if somebody goes out and does power factor and capacitance testing, if somebody goes out and does a thermal scan, all of that information can be constantly updated by these embedded algorithms, and then what you wind up with, you're able to understand if your green transformer is going toward red, or if your maintenance actions that you've taken has actually helped that transformer to become more reliable. I'm waiting for this slide to change. Try it again. Okay. And then what happens is we have processes today that through this linked data, they're able to send out text messages, for example, if low-level things are happening, let somebody know. To broad-based, if serious issues are starting to occur, we can email the whole organization or whatever group the customer decides should be folks taking action on the particular transformer. Trying to get to the next slide. Okay, there it is. And again, I want to emphasize online data needs to be accommodated at the frequency it comes in. I mean, most of the DGA systems are taking samples on like a 4-hour basis, although I think many are user configurable. But, you know, it was done or is done on many transformers today to whatever automated system. And they can be basic systems like GE's Hydran, all the way up to the more sophisticated systems like the Kelmans and the Serverons and other folks' systems that I'm going to offend by not mentioning, and I'm going to apologize for that. Again, you know, you look at your algorithms. We've embedded actions so that as we have trending occur in the gas generation, we're able to take immediate action on that. So if you have an online system, and even a basic Hydran at least tells you hydrocarbons are changing their rate of generation, and you need to correlate that back. It could be because it's just that time of the year and it's running hotter, and we've got some data. So you need to know your long-time trending, and that's really the value of this stuff, is that these databases and quantity of data that we're dealing with. I used to think, well, actually, I used to think a megabyte was a big amount of data, but as life's gone on, gigabytes and even terabytes, and then now we're dealing with petabytes of data. So we're dealing with monstrous amounts of data being generated by these things. If you simply take a look at 2 points, you don't get much of a trend. But as life goes on, you want to follow that data, and you say, okay, there's an increasing trend, but it's relatively flat. It's accelerated in the summer when literally our peak demand typically happens in North America, and we see the highest temperatures. It backs off a little bit in the winter, so we're going to see that. But if we start taking action without the knowledge of the long term, we might make an assumption that something is going to bad happen with this transformer, when in reality, when you look at the data, the transformer is pretty normal, and it just had a kind of a hot August where some gas was collected that's high. We've come up with a lot of routines in order to be able to deal with this data. Obviously, least mean square, statistical. We've literally got a whole team of experts that works on this and develops these algorithms. You've seen this slide before, but what we want to do is show you that if you're constantly looking at this data and you're constantly going through, and every time new data becomes available, you can see there was a transformer, you took an action and got more reliable. We've now got other transformers that are getting less reliable, and then another one that got more reliable. So again, you're able to correlate the actions and the situations happening on your transformer, and we're able to determine that you're taking the right actions, you're behaving the right way to maximize the life of your transformer. What you need to do, and you can see here there's 161 transformers or assets that this customer has, and you want to be able to drill down. You certainly want to keep your eye on the red and the yellow transformers, and you want to be able to drill into those transformers and see what their condition is. And so when you drill into a transformer, you can see this yellow dot. That's the transformer we're looking at, and we're looking at trending. We're seeing that this one did happen to have a transfix on it. We are able to look at the information. We're able to see why that transformer is the most unreliable one in your fleet, and you're able to take some actions and try to get that transformer into a better condition. We're using a lot of our own algorithms. We're also using industry standard tools, the IEEE guides. We're using things like the Duval triangle. In this case, we've got type 1 and type 5, and you can see how that little black dot is moving, with the most current reading being the biggest dot and the more faded dots or smaller dots being where it's come from. But you can get an idea what's going on with your transformer once you spot a trend that's a little bit alarming to you. It gives you an idea whether you're taking actions and maybe making the transformer in a little bit better shape, or whether or not you really do need to react to what's going on with this transformer. So finally, we've got a little summary slide here. I hope the takeaway that you get from this little presentation is that maintenance actions should always be driven by the condition of the transformer, that a good condition assessment has to tell you not only that you should be worried, because I mean helping you not sleep at night isn't the goal of this, but that why you should be worried so that you can set maintenance actions to determine what steps you take are really value driven. Because again, as I mentioned, and there's a lot of statistics behind this, tap changers that are serviced, that are re-energized have a big percentage contribution to the tap changer failure pool. So anytime you touch your transformer, I mean, it's hard to believe that something just sits there and hums as a precision piece of equipment, but it is a precision piece of equipment. Any of you that have been to a transformer factory that manufactures large transformers know it's almost a clean room environment. Particles are key. If you open up your transformer, you always risk moisture as well as other contamination in the transformer, and you need to treat it as such. The basic lesson we learned when my company at least started putting together a service organization, it was based on the fact that transformers are getting older. And of course, that's a fact of life. Your transformer today is a day older than it was yesterday. So time is a bit of a factor, but it is not the significant driver, and in fact, it's not the major factor. The major factor is the environment in which the transformer is applied. Your maintenance actions, have they basically taken place so that the transformer is operating as it was designed, and of course the environmental conditions. If you're in the desert of Arizona or southern Florida, you have a lot of life taken out of your transformers in the summer when all your customers are heavy on their air conditioning load and you got high loads in the transformer. If you're in a more northern climate, maybe life's a little bit better for your transformer. And if you're lucky enough to be in Canada, which quite often has a peak load or in the winter, that's actually the most friendly environment for the customer. You're hammering it hard, but it's done when the transformer's got a low ambient temperature. So again, time's the factor, but it's not the only factor. So what you want to do as you support your transformer and try to get the longest life out of it is to have an accurate condition assessment. As I mentioned, our condition assessment program traditionally has been a snapshot sort of based assessment where we'll go to a customer's site, they'll provide us with data, we'll come home and we'll determine what the risk of failure is of the transformer. And again, condition evaluation has to be the thing that drives the maintenance actions that either lower risk of failure or extend the life of the transformer. There are advanced diagnostic tools that if you're a little confused as to what the condition of your transformer is, there are advanced tools today that you can use to kind of fill in the blanks and get more pieces of that puzzle on your desk so that you can assemble them and get a little bit better picture of what condition the transformer is. And obviously where we're going is an ever-increasing iPhone, iPad, online lifestyle, and so the ability to generate data, it's coming as a tsunami toward us, and so you need to have programs and capabilities to deal with that data, because if you're waiting for your poor transformer engineer to deal with literally the terabytes of data that are coming at them, it's not going to happen. So again, current transformer condition and ongoing changes in condition should be used in driving your maintenance and action plans. That's pretty much the last slide. If there are any questions, we'd be happy to entertain them. We've got a question. Is it possible to get a copy of the slides? And I think, Lelania, maybe you can address that.
Yes, absolutely. A copy of the slide deck as well as a link to the pre-recording or the recorded presentation will be sent out after the webinar.
Okay. And then we got another question. I'll just read it straight off. Is this system for my own group of transformers, or is it shared data within the ABB system with the opportunity to learn from a greater population of similar transformers? I guess the answer to that is sort of yes and no, maybe. It is definitely the entire pool of transformers that we've assessed are used in building our algorithms and building what we've learned about how transformers fail. When a customer hires us to do an assessment, they're only going to get detailed information on their own transformers. So you're going to see the details of your transformers. But just like I showed you that slide of the over 3,000 transformers assessed, we will give you an idea where your transformers stand in terms of other, and if you're an industrial plant, if you're a generating plant, if it's a transmission transformer, we can give you an idea where that transformer stands within that general population of other transformers that we've assessed. And I've got a lot of experts in my office here. Anything to add to that? No. Okay. Do I have the opportunity to use this for dynamic loading? Example, loading the transformer according to its current condition and a prediction of its operation. That's a terrific question. And the answer is, of course, yes. Because, you know, any of you that are familiar with the IEEE standards, for example, know that IEEE requires manufacturers to provide you with a transformer that can be short-term overloaded, can maybe be pushed to 40% higher than its nameplate value for a short period of time. What everybody doesn't remember so well is there's a big star next to that your transformer has to be, in essence, in perfect condition. The oil can't have moisture in it, especially the insulation. The solid insulation has to be in good shape and be fairly moisture-free. So the outcome of this condition assessment is going to tell you if the condition of the transformer is something that that is able to support that sort of loading. So the answer is yes. Also, there are monitoring systems available today. ABB makes one called a tech that any of you that come to Automation and Power World will be able to see the tech applied on a transformer and see how it behaves. But it's got a unique ability that you can put in tomorrow's weather forecast, for example, and you can put your commitment to the, if you need to overload this transformer, and if you have the moisture sensors, if you have the data for the condition of the transformer, you can push the load on that transformer above 100% and either not age the transformer abnormally or age it at a reasonable rate. I was running some scenarios for a customer the other day, and they wanted to push a little bit of an overload through a transformer, this may be a weird way to describe it, but I view life of the transformer as a clock that's spinning around. And I'm an old guy, so I think analog clocks, not digital clocks. And what I see is that when the transformer on a cold day and it's lightly loaded, I don't get 60 minutes to an hour. I maybe get 1 minute to the hour in terms of the life clock of that transformer. But on a really hot day, those hands are spinning and you're taking a lot of life out of the transformer. So you can do a loading prediction and find out that in the 8 or 10 hours sequence, or do you maybe age at 100 hours? And again, us transformer guys that are insulation purists and we want to see transformers last as long as ever, they're a revenue producing piece of equipment for you, if you're a utility, if you're an industrial customer. And if you want to take that theoretical 30-year life of the transformer and exhaust it more quickly, but in the course of exhausting that transformer make a lot of money, that's terrific. And so you can do that. But what we do is we're able to do that with some of the knowing the initial condition, and that's why if you're doing one of these dynamic programs with us, we still do an initial MTMP to find out the condition of the transformer, unless you've literally just driven it off the showroom floor and we know it's brand new. But if the transformer is aged at all, we got to come up with a design-based analytical program that also determines what the condition of the transformer is. I hope I've answered that appropriately. Yeah, and of course, you know, we need load data online. Sometimes, often, generating plants are going to know how their transformers are loaded. That's the key part of this equation. We can build the thermal model based on the design of the transformer, but we do need the loading information as to how the transformer was loaded. Does ABB have concerns over reliability for transformers condition which may slip through the system? You know, the reality is that we're constantly changing these formulas. We're doing the best job that we can do with all the data that's been put in front of us. We've got actually some pretty considerable resources behind these efforts, and our assessments, really, we haven't seen anything slip through. There's been transformers fail that are green transformers that might get hit by a lightning bolt or might have a fault on them occur that doesn't get cleared in just a couple of cycles, or maybe a transformer that's been faulted frequently, and every time that lock rotor motor tries to spin, something's happening. But transformers are really pretty predictable animals. They're not too big of surprises. We do see customers, for example, that aren't willing to take their transformers offline and maybe power factor test bushings every 7 or 8 years. In all honesty, those transformers are risky because we're just in a 7 or 8 year time period is just too long to let that go to be able to catch it. Next question. I understand the price will differ from how many units that each customer has on their system, but is there a certain rate that we charge? Sure. I mean, we charge basically for that initial assessment for the transformer, and really, since these transformers, like I said earlier, have their own DNA, we have to spend a little bit of time with each transformer determining what its condition is. And of course, if there's a lot of transformers in one station, that winds up being something where there's just a synergy, and it winds up being a lower cost. How do you assess the risk of short circuit failure? What inputs does your program use? Well, of course, our risk of short circuit failure, if we have the design, if it's one of those 70% of GE and Westinghouse and ABB or ASEA and Brown-Boveri and National Industry or Stromberg transformers, we'll have the design information with that. If it's one that we determine in our initial assessment is short circuit deficient, and we're doing that generally by groups and types and known issues that manufacturers have, we can then do an in-depth analysis of the risk of short circuit failure where we'll literally take the materials that go into the transformer, for example, the hardness of the copper, and we'll determine what its bending probability is during a short circuit failure. So we'll dig into the transformer design, and I think that's something that does make us unique by having the manufacturing tools to build new state-of-the-art transformers using finite element analysis. And in fact, I tend to offend myself here, and I guess that's an okay thing to do. But I've been around for 33 years in the transformer business, and I started designing about 31 years ago. And I think I was a pretty good design engineer, but truly I was just barely into the calculator age out of the slide rule age. And we had a water-cooled IBM supercomputer at Muncie that had a whole 5 megabyte hard drive. And so the ability to analyze back then just isn't where it is today. I'm sure everybody on this call has a laptop sitting by their side that has way more power than that, and in fact our engineers can do a complete modeling of a transformer, and once the model is built, we're able to do an analysis in just a few seconds. So again, you know, there's just tools available today. We're using every one of those tools we can. If you've done an analysis on the memory needed for storing all this data, and if so, what is your recommendation for the memory space needed on servers to handle all of this data? Now, that you're the guy talking right now, this is Craig Stigemeyer, and I'm a knuckle-dragging Neanderthal transformer engineer. But that's a situation where we do have the ability to deal with these petabytes of data. John Vines is sitting here with me. Maybe he can help answer a little bit of that question.
Well, a lot of that data is data that comes from things like your SCADA system and your Pi historians and things like that. So a lot of that data is already being stored, but for what's not being stored, for solutions similar to ours, we have our own internal data warehousing system that it really depends on, as far as the amount of storage and that goes, it really depends on the amount of data that you have coming in and the frequency at which it's coming in. So if you've got a lot of online sensors on a large fleet, you're obviously going to have a lot coming in on a pretty high frequency. So that's obviously going to require more and more storage space. But today, with the price of storage space, you know, that's a pretty reasonable cost. It's not bad at all. But you know, I think it's going to vary for everybody. If you're mostly an offline test type data situation where you have a lot of DGA tests that you use and power factor tests and things like that that you want to put in there, then obviously the frequency of that data is going to be a lot lower, and you'll have a much smaller need for storage.
Maybe you should mention, John, the size of the installation that we are doing this right now. Number of transformers, for example, it's a real case.
Yeah, I mean, I think, you know, we've got an installation that we're working on right now that includes a pilot of a little over 100 units and eventually goes up to over 1,000 units. But you know, right now we're looking at you know, much under certainly just a terabyte. I mean, it's not a significantly large amount of data even for that size of a fleet. But at the same time, you have to understand that as time goes on, you add more online monitoring systems. Those monitoring systems require more data, and I think you need the ability to scale as you go on so that you can add more storage as it's needed.
Very good. Thanks, John. Again, question about is it possible to obtain a recording of the conference? Lelania, you said the participants would be sent a link for both the presentation and a recording of it, right?
Yes, that's correct.
Okay. And then a question, is there a subscription cost to update the software algorithms from year to year? And the answer is yes, that as I mentioned, we're constantly learning about transformers. Sometimes, and in all honesty, I told you earlier that there's a little over 60 different parameters that we look at. That number didn't used to be more than 60, and it's a number that's changed as we've evaluated more and more transformers we've seen. I mean, and we do have 4 repair shops here in North America, so we see a number of ways transformers break. And so we're constantly asking ourselves, would our algorithms had predicted this transformer as being unreliable? And so the answer is yes. There's a subscription as part of this that would let us take those lessons learned and basically continually update them, roll them out. John, yes?
There is, and in our case, it's really referred to as a maintenance program. And in that maintenance program, not only do you get updates to the various algorithms, but as new sensors come onto the market, we think it's important that if you're part of that maintenance program, you automatically get any new algorithms that are associated with new sensors and new monitoring devices. So basically, the maintenance program covers not only new algorithms and updates to those algorithms, but it also covers any updates to any software that's involved at the same time.
Experience, can utilities provide inputs readily for the modeling, or is the decision purely based on known type issues and design parameters?
I think it's probably a combination, and I think the nice thing that we found is that, you know, the more data that you can provide, the more comprehensive the assessment can be. We can perform an assessment with a limited amount of data, but the certainty of that assessment, obviously goes down a little bit. But the more data you get, the more data you add to that, the more data that can be provided, the confidence level of that assessment goes way up. So it really depends on the amount of data that can be provided. But for the most part, you know, it doesn't require online sensors to do this. I think it's important to understand that. A lot of the testing that goes on now, a lot of the information that you already have, can also contribute to a good assessment.
Would you allow me just one quick
Sure.
comment? Fundamentally, our solution is not creating the need for new data. What the solution is doing is to make sense of the data that is sitting there already somewhere in the infrastructure, in the IT world, in the data repositories, sensors, wherever the data is sitting. What we are doing with this effort is to help the user to make sense of all those terabytes that are there already. So we are not creating the need for new data.
Okay, we got a question that if you're interested in this, do you call me or do you call your friendly local ABB salesman? And it's always best to start with whatever your front-end sales contact is for ABB, however ABB goes to market through you. Starting that discussion, they will quickly get us involved in this. And then a question that is this a system which gives clear actions and recommendations. Timers who had the experience to know what to do are retired, and all the newbies aren't staying for the long term. I think that's a statement I've heard from multiple customers, or something like that. And the reality is, yeah, that as I mentioned, a good condition assessment program has to give you actions to take, has to make recommendations to you. It can't just put that red stoplight in front of your eye and say, what do I do? Because to your point, whoever asked this question, it may not be knowing exactly what to do just because the transformer X is unreliable. So yeah, for sure you want to make sure the system, however you assess your transformers, obviously we'd love to help you assess your transformers, but you need to have a process for taking action. And the final question that I see here, and I guess Lelaine is not going to beat me up because we're finishing about on time, is that have utilities been able to provide inputs like number of through, magnitude of fault current, duration, etc., so our model can assess risk of short circuits? And the answer is, when we're doing a short circuit risk analysis, absolutely. That's a pretty deep analysis. That's way more than your initial fleet assessment and determining condition. But you know, if you have a transformer that's in an environment, and for example, steel mill transformers or distribution or transformers that are closer to trees, like distribution transformers, they're going to see more faults. And obviously, if the utility can enlighten this with any kind of information that has to do with the magnitude, frequency of faults, it goes a long way in being able to get to a solid analysis. And Lelina, believe it or not, that is the last question.
Thank you very much, Craig. I'd like to just close today's event with some additional information about the Automation and Power World Conference, March 25th to 28th in Orlando, Florida. The content you've heard in today's webinar is just an example of the training sessions that will be offered at the conference in March, some statistics on the powerful training events that we're assembling. We're providing a number of different registration options for this year's event. You can register for all days or for select days at some very reasonable rates. There's also a free one-day courtesy registration, especially designed for spouses or special guests you'd like to bring, and for those who wish to attend the Technology and Solutions Center. If those aren't reasons enough to attend this year's event, here are 10 more why you don't want to miss. We encourage you to register for Automation and Power World at abb.com/apworld. At this URL, you can also find links to the conference brochure and additional free webinars like the one you saw today that we're offering through this month. We look forward to seeing you at Automation and Power World. Thank you very much for attending today's webinar. When you close the screen, you'll see a short survey of today's event. We would appreciate your feedback and comments. Thank you, and thank you, Craig, as well, for taking the time to educate us